Hey guys, welcome back. We're going to continue talking about hash tables. We're going to be introducing a concept of a linked list, which in a later video I hope to devote a bit more time to. Um, but for now, I think it's pretty straightforward what we're going to do. Um, so last time, I think this is what the function more or less looked like. Let me test that out real quickly. I've got a call hashed. Console.log hashed get prop we're not we're not in the folder. Okay. Make sure this is the right folder. Yeah. Yep. Okay. Perfect. So what we need to do now is handle collisions, and because this array is, in fact, in every programming language, I think technically arrays are static. I don't know what JavaScript does under the hood, but to get to the point where push and pop and shift and unshift works so well. But in other languages, arrays are of a set size. But we have to account for collisions. And so to do that, we either have to resize or each value in the index has to be such that it can take on multiple components. So in an array where we've got 3 items, right now what we have is each item being just the value. What we're going to do instead is have those items be an object. And that object is going to contain the key. It's going to contain a value. And it's going to contain something that points to another object with its own key and value. And that pointer can be null. So this is what a linked list is essentially. It contains its own information and a pointer to another node. And when you don't have arrays, array methods as easily as implemented as they are in JavaScript, this is a pretty good method. It takes a while to implement, and certainly on the side of adding, it can be tiresome to sort of set up. But the response time on finding stuff in a linked list is usually much quicker than looping through an array. Especially if you set it up as a binary tree. So we aren't going to do a binary tree today, though. So what do we want to do here? We want to, and I'm going to do classes today because I'm a bit for. I could set them up as just constructor functions. I don't want. I don't want the methods being inherited by each new instance because that's going to be taxing on memory. I know that there's a way to get around it. I'm just a lot more familiar with what it looks like in just a class declaration. So, list structure, and we don't actually need. Well, we don't need the length. But we're going to do it anyway. If we were using a linked list for its for something more robust with more search capabilities, we'd need something beyond a head. We'd need probably a lot more information to run the kind of things that we want to. As it is, we're only going to be setting up the means to add and find values in a linked list. We're not going to be implementing methods to delete, although we could. We are not going to be implementing. Yeah, I mean it's just adding and finding. Deleting would be the other major operation that we could talk about. There's other things that you can do too, of course, but we're just going to stick with adding and subtracting. So we need to add to our linked list. So a linked list is its own class. To go back to our example, this is not technically an accurate depiction of what's going to happen. What's actually going to happen is that it is going to point to an object and that object contains information. The most important information is where the real information starts. So there's a class that we've instanced that says, this is where the information that I actually store starts in memory. Go there. And that head is actually going to be what's called a node. And that's the thing that's holding the key, the value, and the pointer. So we're implementing a linked list. We're going to have to implement a node as well. So we'll say let node equal new node key value. Go ahead and value. Okay. So what are we doing here? Sorry, this is this dot next. We're going to create a new node right here. That is going to store the information of the key and the value. It is also going to contain a reference to the next node in the list. If there is no next node, that is going to be a null value. So it won't go. So when we're looping through, what we're going to do is we're going to check to see if the current node that we're on, we're going to see what the property of dot next is. If it's null or if it's a nullish value, then we're going to stop. Well, we don't actually have any error handling for if the property we're trying to access isn't there. But if it's null, we've done goofed. But as long as it's not, we're going to keep on going. We can implement. We can probably implement something like that to handle uh, if there's not a property in there. I'll think about it when I get to it. Okay, so let node if head equals null, it's dot head equals node. That is fairly straightforward. If the head of the linked list that we've instanced still equals null, then we don't need to go to the end of the linked list to add more values. Pretty straightforward. If it's not null, though, then we need to go to the end of it. And we'll say let current node equal its dot head. And while node dot next. So what this is checking for, this while, is checking to see, it's looking for to make sure that there's not a null or a falsy value, not a nullish value, a falsy value. This dot next is only ever going to be set up to handle either null or a node object. Our code is not set up. In fact, if it's anything other than those two, we've done something wrong. But the way we've set it up is to take a node object, which is truthy, because it's an object. Even empty objects are truthy. And null, which is falsy. So if current node.next is truthy, and it will be if it's a node, then we're going to keep on going and check to see, or we're going to check until it's falsy. Then once it's falsy, we know that we have the correct place to insert our new node. So we need to continue going through. So we'll say current node equals current node dot next. Makes enough sense, right? That seems pretty straightforward. And then current node dot next equals node. And since we have a length property, let's say this length. A length property is useful for getting the size of objects, kind of like array.length, right? If you wanted to get the length of the linked list, this would be an easy way to store that, because otherwise you have to go through and count each time you want to get it. It's easier to just store it like this as a bit of information that's easily accessible. So that's how we add. What about finding? Well, I think, yeah, so we pass in key here. So you'll notice add takes in the key value, and get takes in, and find value is going to take in the key. The add is basically going to do the work of setting the property. This is no longer going to be this dot table index equals value. It's going to actually be, it should be dot add. And we're going to take in the key. We need to put the key in with the value when we're storing it. That's actually something that I didn't cover. So before, See, how do I clear all this off? Okay. Excuse me. So before, the way we had it was we had our array item. It's not as thick as it was before. Item 1, item 2, etc. Now, as long as there were no collisions, we had no problem handling it that way. Now that we have to account for collisions, and because we've set it up the way that we have, we need to do it differently. And because we're implementing it with a linked list, there are multiple items stored at each index of the array that we have, the hash table, if you will. And so the first thing we need to do is find which index that we need to go do in that array. We do that with the key and by hashing the key. Then once we go into that, we've got a linked list that we have to sort through. And how do we differentiate the different properties stored in that linked list from one another? Well, we can just store them with their key because we know the key is supposed to be unique. If we want to reset it, we need to, do something for that. We're not going to worry about that now. We can talk about resetting property values for linked lists when I get to linked lists. Let's just worry about adding values for right now. So, okay. So that equals dot add with the key of the value. So now we're implementing the find key or find value. And what do we want to say? Let current node equal head. This dot head. Well, node key does not equal key current node current node dot next. And then we return current node value. Perfect. And then that's not what we need. We need find value. Okay. See what this looks like. Ooh. What did I do wrong? That's what I did wrong. Oh. Array. Let's do 53. I don't know that 53 is prime. It doesn't really matter for our purposes, but Proppy is short. Yep. And then let's just console.log hash. See what that looks like. Oh, interesting. It's passing in the length value to. Yeah, so we don't actually want a length value. Well, I guess it is kind of useful. It's returning the length value of each of the linked lists is returning. So let's see. Find one where there's definitely there's definitely a more straightforward way to do this, but that is interesting. Well, I don't know what's going on, but my concern is that because they're all sharing the same length, they're also going to be sharing the same head. So I don't know. I'll have to look into that and that. Okay. Yeah, so it is just one giant linked list. Okay, I'm gonna have to figure out how to fix that. All right, I'm back. A quick little search through Google revealed the solution. So dot fill is just going to, if you pass in an object there, it's just going to pass in copies of that object to each of them. In fact, if I did something like let one equal prop one a prop two b, let two equal one. This is just going to create a reference to object one. So if I change prop one on object two, it's also going to change prop one on object one. If I change the property on object one, if I change property two of object one, it's going to change property two on object two. There are different ways that you can create copies of objects, which wasn't going to be the purpose of this, but if you only are dealing with strings and numbers, the quickest way to do that is to do json.stringify json.parse. That is the easiest way to just create a new to create just a copy of an object. If you're dealing with things that aren't, I guess, objects, like just straightforward objects like this, not special instances. If you're not dealing with date objects, for example, you're just dealing with strings, numbers, Boolean values, maybe, I don't know, arrays, and arrays containing only those things mentioned, you should be okay. It can't handle, I know it can't handle date objects, and it can't handle anything you've elucidated as a class. So that's what's going, something like that is going on here, where when I fill it with new linked list, it's just pointing out, excuse me, it's just creating a copy of each individual, or it's just creating a copy to that one linked list. There was only ever one. So now if we go back and put in this dot length, this dot length is still in there. Let's see if we console log hashed. Yeah, there we go. That is what we want. So we can start putting in more properties, and we can start to see, maybe we'll get some collision because this is, well, this is small enough that maybe we get some length twos. Yeah, so the first node has two. So let's console log 0. Excuse me. Hashed.table. Yeah. So the first one is the color D, and then it points to prop D, which is right here. So yeah, that's you and I both learned something new today. This is the basics of a linked list. It's just the bare bones of implementing it. It's not doing anything fancy with it. It's just adding and finding. This is the hash table that we already went over last time. The getting and setting are basically identical, but now we have methods attached to each instance, because it's no longer the value in each item of the array, it is an instance of a linked list. So I hope you guys enjoyed the video. As always, please do like, comment, etc., etc. And let me know if you want to see anything else.